Hi everyone. um, I hope you can see the board quite clearly. We've got a few questions here to solve. We are still on time complexity function of algorithms. We're still on that topic. That is a problem we started the last time. We haven't completed it yet. But just for your information, if you want to watch the full videos of these lessons, you please follow me on YouTube channel. If you are on the YouTube browser, you just go to the chat tab and then you type this name, MUNIRRMKTURAY. Then you will see the videos there. Then you can choose which one you want to watch, because on Facebook and other social media platforms, you can get the full lesson. Time is limited, there's space, I know. So now, let's see what these questions say. The first question here says, let h of n be the value of the variable count. That algorithm we saw before, it has two counts, count 1 and count 2. So let that variable h of n be the value of the variable count, which is output when the program pilot is run with input n. They say find in terms of n an exact expression for h of n. That is the function for the time complexity. Simply they ask you to find. So that is number one. Number two now says either h of n in big O of g of n or g of n is in big O h of n. These are two functions. The first function we got before for the program high up was g of n. Now the second function, they ask you about the count. We shall see the program and we will understand what you are trying to say here. Now, question number three. Question number three says, suppose we change the instruction on line 5 from for k equals 1 to n do to k equals 1 to j do. So I just restart one. Oh, time is precious. Do. On line 5, suppose they change the instruction from k equals to 1 to n do, then to k equals 1 to j do. Is the time complexity still of order theta n squared? So let's see how we go about these problems. Let's turn the board so that we can be able to see our code. This is the code, time complexity function of algorithm. The program here, we call it pilot, and the input is integers, positive integers to be specific. That is 1, 2, 3, 4, 5, 6. That is the input. So here the program runs, count, line number 1, count is 1. We've solved this before, part of it before. Now we're going to solve the rest of the questions. So the question says, let hn be the value of the variable count. So we are looking at count. Where is count? If line 1 is count, we got line 1 here as count. We also got line 9 as count as well. Line 9 says count is assigned, 2 times count is assigned to count. This is an assignment. This also is an assignment. So, but if you can see, line 9 is an is being affected by the outer loop. This line 9, there is an outer loop here. J equals 1 to n. Line 9. While line 1, it hasn't got any loop. It just constant function. So, how do we start solving this problem? This marker might have reached its lifespan. For line 1, initially, count is assigned to 1. Yeah, this is assigned to 1. Here, count is assigned to 2. You can see that count 2 undergoes some iteration. Yeah, the program will keep on running here because it's in the loop for j equals to n do up to n do line 12. So this count here is in a loop. So it means it keeps on iterating until a certain condition is met. That is this condition here for j equals to 1 to n. It depends to the input value, which is n. If the size of n is big, so it means this loop will keep on going on and on. The iteration will take some time. So we don't know how many times. That's what we are trying to find out here. So initially, count 1 is assigned to 1. Now count 2 is assigned after iterations. Now, this is after iterations. Count is now assigned to 2. You see here, 2 times count. By how many? You can see it's double. You can see that. But by how many times? It's double by n times. So it's doing it exponentially. It's doing it exponentially. So now, this one here, we can transform this 1 to 2 raised to the power of 0. One of the laws of indices. You know, any number raised to the power of 0 is 1. If you have 100 raised to the power of 0, this gives you 1. If you have 20 raised to the power of 0, this gives you 1. These are just fundamental laws of mathematics. So 1 will transform it to 2 raised to the power of 0. Right? So after n iterations, we now have h of n is 2 raised to the power of n. So h of n is 2 to the power of n. After n iterations, this function now will take an exponential function. That's what we got. That's the answer for the first question. So now let's look at the second question. What it says. Let me read the second question. The second question says, either h of n in big O g of n or g of n in big O h of n. Let me write it here. H of n, big O g of n, or g of n. These are functions, yeah? G of n is in. This is a mathematical symbol, which means it's in. Or G of n is O, big O, h of n. When we solve this problem, g of n, we got g of n to be what was it again? G of n was 2n squared plus 3n plus 3. This is what we got for g of n. Yeah? Initially. And this is now h of n. So now we've got two functions. So what this question now is asking us to do are either is h of n in big O g of n, or g of n is in big O h of n. We have the functions here. These are the functions they are referring to. Is this in this one, or this one in this one? Explain. So what they are trying to ask us here is simply trying to find out the asymptotic behavior of each of these functions. What that means, if you keep on adding the inputs, or you keep on enlarging the inputs, you keep increasing this n, you make it bigger and bigger and bigger, how is this function going to behave with respect to this function? Or how is this function going to behave with respect to this other function? That is what they are trying to ask you. That is what they are trying to find out. You compare the two functions, and then you see how each one is going to behave with respect to the other one. That is what we call the asymptotic behavior of a function. Respect to this case. It's a topic we haven't covered. It's a different topic. When you want to do asymptotic behavior of a function, you normally consider limits of that function at that particular point you want to find, or that particular value, or close to that value. Because when you do limits, you find a value close to a certain value. That is asymptotic behavior. So if you can watch here, what is h of n? H of n, we know h of n, this function, is 2 to the power of n. If you keep on adding n, this value n, if you put n equals to 1, you get 2. What about n equals to 2? You get 4. If you put n equals to 3, you get 8. N equals to 4, this number will keep on increasing exponentially. So, which means, if you take the limit of this function, when n approaches infinity, this function is going to be what? And again, if you look at g of n, you keep on increasing n, and you take n when n is very large, when n is approaching to infinity, this function is going to be what? Then you compare the two. So what we do, we take the limits. We just say lim, mat, L-I-M. The limits of, because we are comparing h of n, is in g of n. The limit as n approaches to infinity. This is how we write it. As n approaches infinity, g of n all over h of n, what would it be like? Which method will apply here when you have something like this? You want to find the limits of two functions, compare. So if you can watch, there are so many methods to use when you're trying to determine the limit of a function or limit of functions. But you look for the one that is most appropriate, or the one you think will save you time. and save you stress as well. Here, if you look at this function here, you can see that if you differentiate this function, what would you get? The limit will still go to infinity. If you differentiate this one, what will you get? The limit will still go to infinity. So in that case, we have a rule we apply to find the limit of these two functions, which is called L'Hopital's rule. L H. Let me look for the spelling. H-O-P-I-T-A-L-S. It's capital. This is a French mathematician, anyway. He invented this rule. So now, as n approaches to infinity, g of n is what? If you differentiate g of n, let's say you differentiate g of n. G of n, what do you get? You get 4n plus 3 if you differentiate this. Now, if you differentiate h of n, what do you get? You get 2, the ln of 2 to the n. If you differentiate this, you get 2 to the ln, natural logarithm of n. When you differentiate, that's what you get. When you differentiate this, you get 4n plus 3. So now, the limit, we are using L'Hopital's rule. So what we do, we find the limits. We differentiate the functions, and then we still try to find the limit. So, now, the limit of g of n, the limit as n approaches to infinity, we have now g of n all over h prime of n, which gives us the limit as n approaches to infinity, g of n, which is 4n plus 3 all over 2 the natural logarithm of 2 to the power of n. So does this help us? We still have here, when n approaches to infinity, this number is going to be infinity. It's going to be large. This other one is going to be infinity. So according to L'Hopital's rule, that is why we have chosen to use L'Hopital's rule, because it gives us the condition of differentiating twice, which will help us. So if we further differentiate this to apply L'Hopital's rule, yeah, if we further differentiate this, where should I erase now? Let me erase here. Now we have h of nn. This is equals to now 2 times the ln of natural logarithm of 2 to the power 2, and g of nn, now you have 4. You have 4. Now these are 2 to the power of n here. Don't forget. Yeah? So we apply the L'Hopital's rule again. We can now erase this one here. G of n, and now we'll have the limit now as n approaches to infinity, g of n all over h prime prime n. This now will give you 4 all over, you have 2 to the power of n, the natural logarithm of 2 to the n all squared. Correct. This is what we are trying to look out for. Now we've got a constant here at the top. Now we have a constant. Had we gotten a constant at the bottom, is also fine. But fortunately now we got it at the top. So what this tells us? This tells us that if you are dividing a number, yeah, this is a smaller number now, 4. When n keeps increasing, this number is going to be very large. Very, very large if n keeps increasing. Let me make this video see myself. So it's like you saying 1 divided by 1,000, which is almost 0, because it's going to be 0.000. So it's almost 0. So what happens here? Now you get a 0 here. The answer is 0. When we use L'Hopital's rule, you got 0 here. So what does that tell us? What does that tell us? Because we got a 0 here, according to some rules, it means now h of n is in O G of n, because it's 0. Yeah? This is what we got. Because it's 0. So this condition holds. The next one says fine. So we've proven the first one, yeah? So let's see what the second one says about this. Now we need this one. This one is done. Let's see this one. G of n. Now we have the limit as n tends to infinity, h of n, g of n. So again, if we differentiate just what we have done, we'll do the same thing again. So we're going to end up with, this time around, we're going to end up with if we differentiate here, h of n, we get 2 to the natural logarithm of 2 to the n all over. If we differentiate this one, we're going to get 4 to the n plus 3. If you further differentiate, we are looking for something like a constant, if it is possible. As n tends to infinity, h prime prime of n all over g prime prime of n. This simply means we are differentiating now twice. That's the meaning of this. So now you get 2 to the n, the ln of 2 to the n all squared all over 4 n, because it was n squared, 4n plus 3 all over 4. All over 4. So now we've got a constant. Once we have this constant, then we can see what happens when n becomes bigger and bigger and bigger. What do you get here? You get, if you say like 4 divided by a million, still the number you get is still big. You divide a million by 4, you have 1 million, 1, 2, 3, 4, 5, 6 by 4. Still the number you get is big. Here we are talking of really massive numbers. So what happens here now? You're still going to get infinity as your answer. Your answer is going to be large if you keep on adding n, the input. If you keep on adding this input, the answer is still going to be large, so you get infinity. So because you get infinity here, it means this one here, g of n, is not in O h of n. That question is answered because you're getting infinity here. First time we got 0, so this condition holds. Second time we got infinity, so this condition doesn't hold. Okay, now let's jump to the next question. Let's jump to the next question and see. And I think that will be the last one for this topic, for this problem. And markers. It's good. The next question says, suppose we change the instruction on line 5 from k equals 1 to n do. So this line 5, we are changing this instruction here from k equals 1 now to k equals 1 to j. K equals 1 to j do. The question says, is the term complexity still of order theta? This is theta of n squared. If we change the instructions, from k equals now to k equals, from k equals to 1, so k, fine. So what they are telling us here, now still, if we are looking at this condition they have changed here, and for this high up, so we can see because this condition is being changed, high up is going to be affected by this change, and we have high up here on lines 6 and line 7. So what that means to us is from k equals to 1. We now have for the outer loop, which is j equals 1 to n, and we have another, that inner loop from now k equals 1 to j is 2. This is what the question says. Is this bright, this ink? Sorry, I'm using red ink so that you can see properly. Because this condition is being changed, we now have for lines 6 and 7, the sum, this is summation sign, j equals 1 to n, This is for the outer loop. Now the inner loop, which has been changed from k equals 1 to j, and high up, we have two high operations here. So 2, this is what we have. So all you need to do is just to find the summation. That's all you are required to do to prove it. So for this one here, you now have n j equals 1 into finding the summation of this k from 1 to j, you just got 2j. You know how to do this now? Summation. This is another topic in mathematics we call series and sequences and summation of series. We shall cover that topic in a later time. So how do we solve this one here? This is a constant, so we can bring it at the front. So now I have 2 summation n to j equals 1j. So what this tells us, this is telling us to add the first natural numbers. 1, 2, 3, 4, 5. Summation of the first natural numbers. We know that formula. That formula is equals to, we have these 2 here, don't leave it. And then what this sign is telling us, this is summation of the first natural numbers. If you're adding 1 plus 2 plus 3 plus 4 plus 5 plus 6, blah, 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 blah. This is the formula, n into n plus 1 all over 2. If I ask you to add these numbers, this is the formula. So you can see this cancels this. Now what do you have? You have n into n plus 1. If you expand this, you get n squared plus n. So because we have n squared here, it means theta n squared is proven. N squared here. Is that the question? Yes, it means theta is in, it means now big O is n squared. Hence this theta is proven. So this question now is complete. We've completed it. Yeah? Thank you for watching. Bye-bye.